Now, you can solve for method 2. You can do that. What you would do, though, in each of these cases is just algebraically, you'd have to plug in the friction for each case. And so, not to belabor the point, but you'd have to change each of these statements again. You'd have to include the friction in each of these statements. And you'd have to plug that in and do the substitution. So then this thing over here would have the following. And then once you get there, you'd have to plug that in over here. And that would change the look of this. And then it starts to get messy, doesn't it? Because you'd have to plug in that information. So let's just let's entertain this idea for a minute. Just gets to go. Get rid of this. So, oopsie. I did put this going. All right. And I forgot that this the force of, like you did again, give it some more room. And you can see it gets a little messy, and we didn't even substitute yet for the friction values. So, I'm going to kind of, and it's going a little long here, it's getting a little boring, a little stale, and I do apologize, but this is the nature of the problems. This would be mu, k, m, a, g, right? So, because mu times Fn, but Fn is going to be equal to the weight because we don't have anything pushing at crazy angles. Ma over mb. And then Ft minus mu. And then, of course, you can plug in numbers as you go instead of keeping all of these letters. But there's a lot of problems, and a lot of problems in the books and explanations where they keep everything in letters. So it looks really ugly right now. It looks really ugly. But you can plug in the numbers and solve this. And if we do that, I'm telling you, it's going to be 10.0 NSFT minus 0.2 20 MA is 1.0 9.81 equals 1.0 over 2.0. And I'm running out of room, so I'm going to take all this and I'm just going to scooch it over a little bit more. Ft minus 0.20 2.0. Wow, still running out of room. .81. And if you solve all this, you will find that Ft equals 6.67 newtons. If and it does, there are some rounding issues. So at one point I did it and I got 6.54 because of rounding, but it should be the same. So be careful if it's roughly, if it doesn't quite match exactly, but it's close. It's because of rounding, and that's fine. And then of course, what you can do is if you plug that, because again we had taken this acceleration and we plugged it in here, and if you take this value and plug it back and work that out, we can say, okay, well 6.67 minus, now again, friction should be mu 0.20 times the mass of B, which is 2.0, times 9.81, because that's the weight of B, all over the mass of B, which is 2.0, equals acceleration. And if we do this, 1.37, which we had already solved for before. Okay, so method 2 looks like a pain. You're like, why would I want to do that when I can do method 1 and solve it easier? I'm going to tell you that there's going to be some problems in your future where method 2 is the only choice to use, where you're going to substitute one equation into the other. And yes, again, you can, choose to plug in numbers here as you go rather than having all these letters floating around to kind of simplify it. And it becomes more of a math game here, doesn't it? Like this just looks like a bunch of math. It doesn't even have physics involved anymore. But don't forget what's going on with the problem. Don't forget about the physical nature of the problem. That you're pulling an object, it's scraping across the floor. The tension between the two objects is the same between the two objects because of Newton's third law, and so forth. Okay, so that's a lot to process. The last thing I want to mention is that these kinds of problems are very, very similar to when you have something being lifted by a force that might be connected to something else. And so if you have mass A and mass B, and there's some kind of upward force, now that upward force could pull the object upward. That upward force could just be a force preventing it from falling. So that acceleration could be upward if we are pulling with more force than needed, or if we're using a force that's just preventing it from going into free fall, but still letting it fall. The acceleration can be downward. And what you have to do here is, same kind of argument. Do we want to have the entire system move as one? Which is fine, but then you cannot find the tension in between the objects. Or do we want to treat the two objects independently? And if you treat the two objects independently, of course, you have to do the free body diagrams for each object. And we can do that. For object A, we're going to have force upward, because that force is only acting on object A. It's not acting on object B. And of course, there's the force of gravity of A, because A has its own gravity. And of course, there's the force of tension between the two objects. There's no friction or anything here because these are two objects being raised in the air, right? So we're not going to have any friction involved. But the weights are involved now, unlike before, because the weights were not involved because they were in the other direction and they were being balanced by the normal force. In this particular case, we're going to have that force of tension. Now that force of tension, again, is equal but opposite. So that's the same Ft value. And then, of course, object B has to worry about its own weight. For a lot of students, for whatever reason, they want to say that the gravitation of B is the tension. And I understand why that is, but that's not true. Especially, well, it's not true if you're accelerating. If you're standing still, that will be true. If you're standing still, the tension will be equal to the weight of B, but not if you're accelerating. And so don't make that mistake. And don't make the mistake of thinking that the weight of on A is the combination of these two. That's not true either. Because remember, when you do a free body diagram, it is only the forces acting on that object directly. Right? So when you look at object A, you have to isolate it and say, okay, well, what forces are acting only on A? Well, A has the tension here. A's got a tension. But A has its own weight. And A has the upward force. And then when you look at object B and you isolate it, you look through the eyes of B. Well, what are the only forces acting on B? Well, B has its own weight. And the tension is pulling it upward. So you have to be very clear. And then once you do that, of course, you can do your summations of the forces for each object. Or you could do the summation, summation of the forces for the overall. So you have to make those choices. Okay? So, that's a lot of information. I hope that was enough.